Hello and welcome to the lecture Introduction to Deep Neural Network Part 3. In this lecture, we are going to discuss the training procedure of the deep neural networks. And then we discuss why deep neural network is successful nowadays. Then we try to understand what are the main characteristics of DNN and we conclude the different types of DNN. So as we have discussed in our last lecture that until recently we don't have very good training algorithm for deeper networks. So the major breakthrough is coming as in 2006, this Hinton et al. Invented a algorithm in their seminal paper reducing the dimensionality of data with neural networks, which essentially made this breakthrough. So here what the major thing we observed that this algorithm give a very good solution for the vanishing gradient problem, which was the one of the most important bottleneck to use the backpropagation like algorithm for the deeper models. The name of the proposed algorithm, bit simplistically, is layer-wise pretraining. So first of all, in this lecture, we try to understand why is layer-wise pretraining. Okay. Now, what is our goal? We have a big network because these hidden layers are, this number of hidden layers are very high. So, vanishing gradient problem, what I have discussed before, becoming a very important bottleneck. What was happening that when we at the output layer we formulate or we get the error gradient, and this error gradient is basically back propagating from output layer to input layer, and the back propagation algorithms use the successive differentiation using chain rule. And what happened during this successive differentiation, then this error gradient are decaying, and when it come to these initial layers, the error gradient become very close to zero. So the weight updation becoming almost negligible, or there was no weight updation at all. Since this, you can see the gradient is decaying, so vanishing, that's the name, vanishing gradient. That was the main problem. Now what Professor Hinton and et al. Suggested that we train layer by layer. So we are not training whole network at the same time. Rather, we try to train this first hidden layer at the first time. But as we know, if we have to train this layer, we need some error, and then only we can take the error gradient, and accordingly the weights can be updated. But we don't have output of this. In our supervised case, output is only available at the output level. So as a solution, they suggested a very interesting idea. They said they will use the concept of autoencoder. So what is autoencoder? Autoencoder is basically a neural net that reconstructs inputs. Given an input, there was the layer. For this particular case, this is a single layer, and this single layer is going to reconstruct or try to reconstruct this input. Definitely there will be some error, and this error we take as our loss function, and we take the error gradient and using the backpropagation, because backpropagation is very useful here because it is only single layer. There is no vanishing gradient because it is only single layer. So by virtue of this autoencoder concept, we can train this layer. And when it is converged, that we can understand, this first layer is being trained to reconstruct this. Then we make this as a input layer to the next hidden layer. Okay, so the what thing will be coming here after the first layer of training is done, the same process input reconstruction done using the first hidden layer trained as the input layer and next hidden layer as the hidden layer, like this. Now this is your input, and this input is going to reconstruct somewhere here, and this is as your hidden layer. Okay, so this is the second layer of training, and the same autoencoder thing has been used. Now only difference is that now input is your first hidden layer, there is a second hidden layer, and so this is the first hidden layer for the second layer training. This is your second hidden layer, and this first hidden layer been reconstructed here. Okay, so that kind of is autoencoding. Again, this thing is being used. So we get this, and this process is doing or repeating up to the output layer. Okay, so we can get last layer training also. So in this way, very successfully, all the layers are being trained without the problem of vanishing. Okay, so that was the basic idea of this particular paper. Is quite complicated, but the takeaway message, the concept is this. Okay. So now what we understand here in this deep learning paradigm, why it is successful. Nowadays a huge amount of data is available to us, and somewhat, even if it is costly, some data can be annotated. So data availability is one of the major reason why deep learning is so successful today. Now algorithm, after this paper in 2006, we have an efficient algorithm to train the deep models. More sophisticated algorithm proposed after that, but it was just this beginning of an era. And thirdly, what we have discussed, the availability of the GPU computing power. So in last decade, due to the huge advancement in hardware, we have enough GPU to computing facility. So with these three major particles, deep learning is becoming very, very successful and outperform the conventional machine learning in a substantial manner. There are three major characteristics of deep learning. First is hierarchical compositionality. Next is end-to-end learning. And third is distributed representation. We'll see one by one. So, first of all, what do you mean by hierarchical compositionality? This essential make this neural network capable to learn the representation where higher level concepts are composed of lower level features. That means there is in deep learning, the higher layers, whatever feature they are modeling or their automatic feature extraction, what feature they are extracted is basically based on the lower layers. And this is a design in a hierarchical way. So there is some hierarchical composition is built up. So you can say that this higher layer concept or these features are basically based or composed of the lower layers and organized across layers. So this is the idea of hierarchical composition. So that we have already said quite a few times that the local patterns like pixel or edges is modeled by the initial layers, initial hidden layers. Then intermediate layers combine these pixels and edges to get more abstract structure like corners, texture, parts of the objects, something like that. And then again, these middle level neurons are combined to form deeper layer representation that represent more complex and semantically meaningful entities like objects or scenes. And this is basically the hierarchical representation across the layers, which is called hierarchical composition. And that makes the difference that these deep learning architectures are going to model the very complex task very easily or very accurately. So this hierarchical compositionality makes deep learning developing abstract or invariant features to enhance its ability for better understanding this sequence. Sequence, why sequence? Because there is a sentence. Okay, that's this. There is some contextual meaning of the sentence. Okay, to understand this context, it's a very complex task. So this kind of understanding very easily done by deep learning because of this hierarchical composition. So invariant features to enhance the ability to better understand sequence, language, complex data like very complicated images, enabling efficient learning and generalization. Okay, so this got the composition, hierarchical composition. Next is the end-to-end learning. So basically, you see, there is the input to output. There is no intermediate manual intervention. So in end-to-end learning, trains a single model to map raw input directly to the final output. And that is a very fascinating characteristics of the deep learning. So it's a direct mapping. Instead of a separate modules for feature extraction, processing network, or some processing and decision making and inference, it learns the intermediate step with a one unified and differentiable system. Most of the cases, this activation function in this feed-forward network, these equations are different. And it's unified, so one structure. Now, this entire system is trained end to end when we use the gradient descent, the entire system is being learned using this backpropagation, adjusting all parameters simultaneously. So weight updation of parameters is not that this model or this module is trained differently, that module is trained in different time. No, it's all parameters minimize the overall loss, making it a brute force but power. Okay, and it essentially feasible, make it feasible, this automatic feature learning. So the network learns the most relevant feature directly from the data. It is not that we have engineered or extract some feature rather than relying on the human design feature. And that is one of the major advantage over the conventional machine learning. So deep learning as an automatic feature learning. The one important aspect here, in general, deep learning required large amount of data, but it achieved a very superior performance. Since data is available today, that's why deep learning is very much successful nowadays. So optimizing the whole pipeline at once, particularly complex tasks like speech processing or image capturing kind of thing, that we have to have this. So end-to-end learning is another major important aspect of deep learning. And finally, distributed representation is also a very important concept. Now, distributed representation in neural network, what does this mean? That this encode some concept, because we said concept, but because this different kind of abstraction, maybe age in a very initial layer, maybe some shapes by middle layer, or some object kind of thing by the final layer. It is not by one neuron, but as a pattern of activation across many neurons. So the thing is that the one pattern is not done by not only one neuron, but a combination. Here, each concept uses a unique combination, and each neuron participate in the multiple concept. So basically, make it a distributed arrangement. And what essentially it happens, it makes the network efficient and powerful learning mechanism for complex relationship like word embeddings or image features. So actually what happened, similar ideas, okay, these similar ideas closer to a vector space, so that is the called re-embedding. We come when we going to discuss the natural language processing thing. Okay, this is different than the local representation where one neuron per concept, they are not using this, okay, and allows the network to generalize better and handle complex data like language division. Because if you use a single neuron, there is a chance of kind of the local concept will come, but here many neurons are used, so the pattern is activation across many neurons, so many neurons are involved for a particular pattern, and so that it essentially improves the generalization better, so that it handles the complex data like language vision. Okay, so these are three main verticals, what makes this deep neural network so much successful today. Now, as a concluding slide of this lecture, in this course we are basically going to touch upon few deep neural networks. for our language and computer vision task. So here we give you just kind of that we try to touch upon. First we start with convolution neural network. Then we go for a sequential modeling, that RNN, weighted RNN, LSTM, transformer, etc. Then we'll go for the generative AI kind of autoregressive models, variational autoencoder, GAN, this generative adversarial network, diffusion model, etc. So these are the main important deep learning networks. Nowadays, this LLM is very much renowned. So these transformers are basically backbones. So that we are going to discuss. So in summary, in this lecture, we basically discuss the training of deep neural network by virtue of the Hinton's algorithm. Then we discuss why deep neural network is so successful today. Then we discuss the three main characteristics of the deep neural network. And finally, we have discussed the different types of deep neural networks. Okay. The next class, in module 6, we start this computer vision. We introduce this computer vision through the machine learning. Okay. Thank you very much.